This is the second module on gas mixtures, and we will look at a particular subclass of mixtures of ideal gases or real gases, which is listed here as gas vapor mixtures. Its particular application is in psychrometry, which is the study of heating, cooling, humidification, dehumidification of air to achieve certain thermal comfort. So, what we will be doing in this part of the study is to look at three general aspects. First, we will study the properties of air water mixture, and we see how which properties are there and how we specify them. We will follow this with a study of the way the properties are plotted, which is the psychrometric chart, and then we will look at some applications. So, to begin with, we will look at what is an air water mixture. Technically, water is the name of the pure substance, but what we are looking at is basically air and a mixture of water vapor. So, this is the air that we live in, we breathe it. So, we have two components coming up here, one what we have called as air, and the second thing is water vapor. When we looked at the mixtures, we recognize that air is a mixture of 21% by volume oxygen, approximately 79% by volume nitrogen, and small amounts of argon, carbon dioxide, and some other gases. So, one thing we did in modeling air was to say that we will make it as a binary mixture as O2 plus 3.76 N2. So, this level of detailing is required, say, when we look at reacting systems, when we ask the question, how does the substance burn in air. But as we also saw, there are many applications where we really do not need to know what the oxygen and the nitrogen are doing. We considered this mixture as some sort of a pseudo pure substance. Which means that we are ignoring that there are two different types of molecules in air. We homogenize them and say, look, forget these two, we will have air only as one particular type of a molecule, whatever it may be, and we will assign properties to it based on what we see as the properties of this mixture. So, this is what got us last time, and now we will treat this as what we are calling here as air. Water or water vapor is nothing but water as the pure substance that has been studied in the earlier modules in thermodynamics. Its properties are exactly, we will be taking from there only. We are calling it water vapor because we are looking at a vapor phase of water mixing with air. So, here is what we end up doing. Having decided that air is O2 plus 3.76 N2, we then start assigning properties to it, which we will require in our study. And the first one is the molecular mass, molar mass 28.97 kg per kilomole. So, we are calling it M air, and this is the gas constant for air, which is 0.287 kilojoules per kg per Kelvin. So, now we have got back our binary mixture of air as one component and water vapor as the second component. Now, in the study of psychrometry, the applications are such that we are working with temperatures typically -10 to +50 degrees Celsius. But that is not to say that this is the only thing of interest and that thermal comfort is the only one that we are interested in. There are situations where temperatures could be much below 10 degrees Celsius. For example, on the Siachen glaciers, temperatures of -20, -40 degrees Celsius are not uncommon. So, the question is that if we have to heat that air, how can we know the properties of that air and then predict how much is the heat release rate that is needed. At the other end, temperatures in excess of 50 degrees Celsius are typical in many parts of India. 55, 56, 58 degrees Celsius are not uncommon in the Rajasthan desert and in some parts of Telangana. So, we also have to worry about these extremes, and there would be some industrial applications where the temperatures could go even beyond this, say 80 degrees, 90 degrees Celsius. The procedure and the concepts and the principles that we will learn here are by and large good for most of that regime. In applications, we will also assume this was the temperature variation that we come across. The pressure variation that we will come across is like 0.5 bar to 1 bar. So, 0.5 bar is like the pressure at about 5,000 meter elevation up in the Himalayas, say. 1 bar is what you would see normally around sea level or in most cases. So, what we do is we say that these are the conditions under which I will have to study the mixture of air and water vapor. So, here is what one can draw is that we make a system where these are the molecules of air, and interspersed within that are water. So, what we are saying is that this is the pseudo pure substance called air molecule, and this of course, there is no problem with this is a H2O. So, now let us look at what each one of these are doing and see if we can make life a little more simpler than. If you look at air and look at these temperatures which are of the order of 300 K and pressures of 1 bar, then we realize that both O2 and N2 they behave like ideal gases. And so, it is reasonably good extension of this to the fact that air, which we have now made into a pseudo pure substance. So, we will model air also as ideal gas behavior. In doing so, life becomes very easy because the equation of state for air is very simple and elegant, which tells you that P v is equal to R T. Now, because we have a mixture here, we need to be clear at every time throughout this discussion as to which is the substance whose properties we are dealing with. Merely writing P and V and R and T does not tell us is it the property of this mixture, is it the property of the air, or is it the property of the H2O. So, we will use some more variations on this, and we will use the subscript A to denote ambient air or moist air. So, A means this is ambient air or moist air, and this air which is inside this. So, this whole thing is moist air, and this thing which is here, this we will now call as dry air. So, if you look at air as a mixture, equation of state becomes P A V A is equal to R, which is the gas constant for air, multiplied by the temperature, or P A times V is equal to M A R A T A. R A we have been using earlier. This is 0.287 kilojoules per kg Kelvin. So, this is what this whole air was, assuming it to be an ideal gas. Now, we look at dry air and say, no, dry air is also going to be modeled as an ideal gas. So, we now have the composition of air or moist air, as we may call it, with a subscript A, or you will find in some books and other references there is no subscript, in which case it is implied that the property is the property of a binary mixture. So, this binary mixture contains two components, which in our mixture theory we can say I equal to 1, which is dry air, I equal to 2 is water. We may call it, some call it water, some would refer to it as water vapor, others refer to it only as vapor, but it is meaning the same thing. So, it is a mixture of these two that we are saying is air. So, we have air or moist air as a mixture of dry air and water vapor. We had seen from earlier thermodynamics, and now that this is reasonably well modeled as an ideal gas. Now, we will say no, that dry air is also the same thing, with moisture gone. This is also behaving like an ideal gas. So, you got ideal gas behavior here and ideal gas behavior here. In a minute, we will see how do we handle the water vapor in air. So, for dry air, we will use consistently the subscript d A, and for water vapor, we will consistently use the subscript W V. You will find that these symbols are somewhat different in different textbooks, but I have chosen these just to make sure that when we use this subscript, there is no ambiguity or clash with a subscript that we have used earlier in the past. So, life becomes a little more involved writing d A for dry air. Some people write just A, others would write only V, but we will stick with this, that d A subscript means dry air, W V subscript means water vapor. So, now we go back to what we have learnt in mixture theory. First property of a mixture is its mass fractions. So, we can say the mass fraction of dry air is mass of dry air divided by the total mass of air in that volume. So, that is what it is, that if we have a system there, this contains some water vapor and there is some moisture in it, dry air, then the mass of the dry air, which is these black dots, divided by the total mass of both in this system is the mass fraction of dry air. And similarly, mass fraction of water vapor is the mass of water vapor divided by the total mass of the system. The same thing can be modified to indicate the molar fractions, which is indicated as we saw earlier with the lowercase y. So, y d A is number of moles of dry air divided by the number of moles of the total number of moles in the mixture, and the mole fraction of water vapor is number of moles of water vapor divided by total number of moles in the mixture. So, basically what we have said here is that mass of the air is equal to mass of dry air plus mass of water vapor, and same thing with the number of moles. Number of moles of air is equal to number of moles of dry air plus number of moles of water vapor. So, this is fairly standard notation that we looked at when you are dealing with mixtures. So, this we can say now that this is a binary mixture. Number of components which we have earlier said was k is equal to 2. So, we can say this is k is number of components and not the specific heat ratio. So, now we say what are the properties of air rather that we are actually looking for. So, like any pure substance, we would like to know the same thing, what is the temperature, then its specific heat, specific entropy, specific enthalpy, specific internal energy, and anything else that is unique to this particular mixture is a series of definitions by which we call humidity. So, what we will do now is go one by one and look at all the properties that are there for air water mixture, or what we may call it just as air or moist air. So, if I use the word air or sometimes I use the word term moist air, the meaning is the same. So, we begin with looking at the dry bulb temperature. This is called abbreviated as dBT and sometimes T the subscript dB. When we write equations, we use this and not this one. So, dry bulb temperature is what it is when we say what is the air temperature, and what we have basically done is we just took an instrument and we just, this was the sensor part of it. So, it could be a mercury thermometer or it could be a thermocouple, either bare bead thermocouple or a shielded thermocouple, or this could be a RTD or any other type of a sensor, but these are the most common ones. So, if this is just sitting in the air or the air stream or a process where the air temperature is to be measured, then by just putting this is the bulb, or you may call it the sensor. The temperature indicated by this instrument directly here or through this on a readout or on a computer these days, this is going to give us the dry bulb temperature. What one has to take care about though in this case is that every time we have something anywhere in the air, there is always radiative transfer between the surrounding surfaces and that sensor. So, if we really want to measure only the temperature of air, we need to cut out as far as possible all this radiation that is happening, which means that if there are other surfaces that are in this vicinity, then we need to make sure that this radiation does not affect this. Because even if there is a small difference in this temperature and say this surface temperature, which could be a wall or it could be the skin of a person or it could be some other engineering device, then this is going to radiate also, and this will affect, this will show a temperature which is not exactly the temperature of the air. So, what we are interested in is the temperature of the molecules over there, and we only want this to be the system, but now there is radiative transfer taking place. So, one of the things that is done is that around this one puts a series of shields, which are nothing but very thin pieces of metal, so that there is no direct radiative transfer from here to the surrounding surfaces. This is particularly true when we are making measurements of atmospheric air, where you have tried to put a thermometer out in the open, and you have to make sure that that thermometer is not exposed to radiation from other surfaces nor to radiation from the sun and also the sky. So, a radiation shield is a necessity to accurately and reliably make a measurement of dry bulb temperature. So, when we measure the temperature of air, this air is moist, it has got water vapor in it. So, what we are saying is that irrespective of how much each one of these is there, we have some air over there, which is these black dots, and we have some water vapor in there, which are these blue dots. The temperature of each one of these species is the same. That means, in moist air, the dry air and the water have the same temperature, which is nothing but the dry bulb temperature. In fact, even in the later analysis, we look at other applications. Wherever we are dealing with the mixture and we say what is the temperature, we will always mean that it is the temperature of the mixture which is in equilibrium, which means that water and air are at the same temperature. There will be no such distinction that what is the temperature of air in it and what is the temperature of water in it. This could be an issue with industrial say processes where one air stream is warmer than the other and the two are mixing, but then our analysis will be limited to the fact that we have finally reached an equilibrium and we are then applying the equations to that. So, there is equilibrium, and the temperature, whenever we talk in this discussion, it will always be same for either of the components as it is for the mixture. So, that is the idea of the dry bulb temperature. It is relatively straightforward, and even if you look at weather forecasts anywhere or what are the weather in the last so many days, it is the dry bulb temperature that people are reporting. And when we talk of climate change and global warming, we are basically saying that what is the mean temperature of air, and in that we are actually saying what is the mean dry bulb temperature of air, and we are looking at a historical trend on that. Basically, that is what we are doing. So, that is the concept of dry bulb temperature and its importance. The next property we will look at is that for dry air, how do we get the specific heats? Now, we recall that we have said that moist air was an ideal gas. So, the first thing is that we say dry air, again O2 plus 3.76 N2 at the temperatures and pressure that we are interested in is an ideal gas, and which means that we can now define the specific heat at constant pressure at low pressures for dry air dA, which is same as what we have learnt earlier. The specific heat for air 1.005 kilojoules per kg Kelvin. This is reasonably okay over the small temperature range. Actually, specific heat of air or any other substance for that matter is a function of temperature. But fortunately for us, our temperature range over which we are doing these analysis is reasonably compact, and so even if you took the specific heat variation across those temperatures and use the temperature dependent specific heat, the value you would get from there would not be very much different from this constant 1.005 kilojoules per kg Kelvin. And this variation is quantified and it is less than plus minus 0.2%. So, we are quite justified in assuming that dry air has constant specific heat, and we will work with that. Now, we come to the next property. So, that was the dry air specific heat. Now, we come to the next property, which is the specific enthalpy of dry air, and this we will use the symbol H with a subscript dA. So, this is same dry air, there is no moisture in it, the pseudo pure substance. It is an ideal gas of this specific heat. So, we can write that the specific heat of dry air, the specific enthalpy of dry air is the specific heat times the temperature. On change in the enthalpy of dry air is specific heat of dry air, which we have said that is constant, and difference of the temperatures delta T. Now, there is an issue in this, that if we are talking of change in specific enthalpy, the reference state to which H is taken from becomes a non-issue. So, here reference state does not matter, it is not an issue. But if you are looking at this and you are trying to make a plot, say H plot of specific enthalpy versus something else, then you have to have some reference state so that you can start putting numbers on that plot. So, you need a reference state. In the tables that we have used earlier, 0 degrees Celsius saturated liquid, the specific enthalpy was taken as 0. That is a completely convenience selection, and people have used different temperatures for different substances. So, absolute numbers on charts may look different or tables may look different, but the differences will always be pretty much the same. The same thing happens later on when we look at the psychrometric chart. When we plot specific enthalpy, we ask, what is the reference state to which we are referencing the specific heat of air, the specific enthalpy of air. The same issue will also come up when we look at the specific enthalpy of water. But for dry air, it is a fairly straightforward relation that is given here. So, now we look at what the water vapor, how to handle the properties of water vapor. So, these are all those blue dots that we showed in those pictures. And first, before we actually go to numbers, let us try to get some idea of what is the order of magnitude of how much water vapor is there in air. And so, what it tells us is that if there is air and the maximum amount of water vapor that it can hold, we all know from experience is the saturation condition. That means, once the vapor is dry saturated in air, it cannot hold any more moisture, it will condense or precipitate or freeze. So, let us get some typical number, and I have taken at 50 degrees Celsius the saturation pressure of water from the steam tables is 12.3 kilopascals, and this is significantly smaller than the ambient pressure, which is 100 kilopascal. So, although not very, very small, but still 10%, 15% in that range. So, what it also tells us is that when we look at water vapor at this sort of a condition and look at the TS diagram, then at low temperatures water vapor is like a superheated vapor. So, here is what we are actually saying now, that if we look at the TS diagram, then on this we can draw the saturation states, which is given by the dome. And now we say where are the states that we are looking at. So, what we are doing is, we said it is, this graph would say get the triple point at say some point here, and then we have the other limits that we are looking at. There is somewhere there is 50 degrees Celsius, say roughly let us call this 50 degrees Celsius, and temperatures could go down -10, -20, whatever it is here. So, we are looking at water vapor in some sort of a region like this. So, the states that we are looking at for water vapor, they are here. So, we are looking at a very small region of the total TS diagram or the TV diagram, if you have to look at that. So, what happens in this case, if you look at this part there, then the lines of constant enthalpy, they are like this. Near the dome there is a slight non-linearity, little away from it these lines are parallel. And as you go further up also in the dome, all the way to maybe 500, 600 degrees Celsius, once you are far away from this region or this dome region or the critical region, H lines, constant isenthalpic lines are like this. So, this is H equal to constant. The other thing we learn from this picture is that all these states are superheated vapors. At the extreme, we could say that these states come onto this line, where we could say that they are dry saturated vapors. So, we know from experience that 50 degrees Celsius and 1 bar pressure comes somewhere over here, pretty much on the saturated liquid line. It is a liquid state. We are at 50 degrees Celsius, but we are in the vapor phase, and that is because the pressure, instead of being 1 bar, is actually much lower. This is, say, the 1 bar line over there. We are over here where the pressure is much less than 1 bar pressure. So, this is one thing. The water vapor that we are dealing with is the superheated vapor, and at most a dry saturated vapor. We are not looking at the fact that some of this has condensed and become, if it has condensed, it will become a dry, saturated liquid there. We are not looking at that. So, that is one. The second thing is that lines of constant enthalpy are pretty much straight. And so, we ask the question, this information plus this, what does it tell us? The question we are asking is if it is superheated vapor, then can I say this is an ideal gas? And if we say yes, it is an ideal gas, then within how much error, plus minus how much? So, the fact that these lines have become constant, it means that for every given t, there is a unique value of H. So, these are all different values of H, whatever we can call it, and say this is H1, H2, and where 1 and 2 are purely numbers that I am using for description sake. They are not states or components or anything like that. So, what this is telling us is that if we know the T, we can uniquely get H in this region. That means, there is a one-to-one correspondence between these two, and that is pretty much of what we saw just now for air, where we said that H is pretty much equal to constant pressure specific heat multiplied by the temperature. So, if we have constant pressure specific heat, this is the same relation that we are seeing over here. So, that is nice to know, because now we can say that given all these things, this superheated vapor could actually be treated like an ideal gas, and that is another very nice thing to have, because it makes the calculations much more elegant. And when we do that, the error that we get in the value of H is less than plus minus 0.2%, and so we are in pretty good shape to say that this air, this water vapor is behaving like an ideal gas. So, that is the second thing that we have just now looked at, and now let us see what are the implications of this thing. Well, the very first thing it tells us is that the mixture that we were talking of right in the beginning is now a mixture. So, what the binary mixture, or what we called as moist air, we call this as dry air plus water or water vapor this has been independently taken as an ideal gas. Now, we have just argued that for the temperature and pressures we are interested in, this is also an ideal gas, and we have also been saying that air, this itself is also pretty much behaving like an ideal gas. So, now our objective becomes to get the properties of this air in terms of properties of these two, which we have just seen can be modeled as ideal gases. So, let us do that now. We will look at air, we have already seen what the equation of state is. We will now see what happens for water vapor. So, what we do, since we have said that to a very good extent water vapor can be said to be an ideal gas, we can write the equation of state as P W V. We are now using the subscript W V wherever we are dealing with water. So, make this very clear then. P W V times V is equal to M W V R W V T A. Now, T A is the temperature of the mixture or the temperature of the air. Subscript A means air, it was the moist air. The correct thing to write would have been that we put here T W V. But just we argued that we are not going to be bothered about the fact that there is a temperature difference between the two components within the mixture. The mixture is in thermal equilibrium, so the temperatures are the same. So, that is what we have put that as T A. We will not talk of this thing at all. And what is this T A? T A is something that you just measure using what we just learnt now as the dry bulb temperature. So, technically this is T dB. So, the thermometer just placed there without any radiation effects tells us the dry bulb temperature, which is the temperature of the air, which is the temperature of the two components. So, we can write this equation as a specific volume thing, and we get the gas constant for water vapor R W V as 0.4615 kilojoules per kg. So, that is another good thing we got. Now, we do the same thing what we did for air water few minutes back. Now, we look at specific enthalpy of water. So, one thing that we can see is that those lines which were going horizontal, these lines, there is a very slight bend near this, and if you go to even lower pressures, and you can actually see the property charts, this line is actually straight right from this point itself. You are basically saying that even though we are very close to the saturation state, the pressure and temperature is such that even the dry saturated vapor is behaving reasonably well like an ideal gas. That is what this chart is telling us. The deviation becomes more as pressure gets higher and higher. So, one of the things that can be done is that we can say that this value of H is approximately equal to this value, and this value is easy to get because this is nothing but the specific enthalpy of dry saturated vapor, which in the past we have denoted by H g. Remember the subscripts F and G. F was for the saturated liquid, G was for the saturated vapor. We are using the same notation now. So, this is H g. So, one can say now that with about 0.4% error, the specific enthalpy of water vapor in the regime we are interested in is almost equal to H g at that particular temperature. So, whatever temperature was there, at that temperature, what is the specific enthalpy of the H g for water vapor? That is going to be the H for water vapor. To get the effect of temperature, which is what we are seeing there happening slightly, we can write H g as H g at 0 degree Celsius plus 1.82 times TA. TA is in degrees Celsius. This comes about from a very small little derivation which is there in the notes. I will not go into the details here, but after doing that, what you get is Hg at 0 degrees C is 2501.3 kilojoules per kg. And so, the equation that we will see being used is that the specific enthalpy of water vapor is almost equal to 2501.3 plus 1.82 TA, where TA is in degrees Celsius. So, that is another relation we have now, how to get the specific enthalpy of water vapor. So, we got the specific enthalpy of air, we got the specific enthalpy of water vapor. Now, we move on to see how do we quantify the composition of this mixture. And like we defined for mixtures in general, here also we define two things, the partial pressure and the partial volumes. So, the total pressure of air PA is the partial pressure of dry air plus the partial pressure of water vapor. And we derived this thing for mixtures, that the partial pressure of the component is equal to its molar fraction multiplied by the system pressure. So, that is what we have here, Pwv is equal to Ywv into Pa. Same thing we can do now with so this is a partial pressure. Now, we look at partial volumes, and what we had done last time is exactly the same thing we are doing here, that the partial volume of a component is its molar fraction multiplied by the volume of the mixture. So, V is the total volume of the mixture, and VdA is the volume occupied by that particular component if it were to be alone at the same pressure and temperature. And the volume of water vapor is molar fraction of water vapor multiplied by the volume of the system. Now, we come to defining a series of terms which are unique to psychrometry, air conditioning and these type of applications. First, we will look at what is called specific humidity. Its symbol is SH, and it is something that is not used very frequently, but it is good to know what it is in the first case. So, specific humidity is mass of water over mass of air, which is moist air. So, what we are saying is we make a system in which we have both types of molecules, the air there and the water there. And what we are saying is that the mass of water in this system, which is the numerator, divided by the total mass that is there here, which is the mass of air, this ratio is called the specific humidity. And although it is a ratio and both are mass, it is not a non-dimensional number, because this is expressed as grams of water vapor per kilogram of air. Now, we can do what we have looked at partial pressures there earlier. We saw that the mass of water in air, this is about of the order of 3% or less. Three percent was at 50 degrees Celsius and 100% humidity. That means completely full of air moisture. But at 25 degrees Celsius and say 50% humidity, which is what an air conditioned room typically would have, this reduces by about a factor of 2. So, it is much smaller. By and large, specific humidity is not used in calculations and not shown on charts, because this depends on the temperature of the system. And so, it is good to know that this is the definition of specific humidity, but also be clear that it is not used. In a minute, we will come back to it for a different reason. The term that is used widely and shown on the charts is variously called humidity ratio or moisture content or mixing ratio. So, this is mass of water in the volume occupied by 1 kilogram of dry air, or what mass of water present per unit mass of dry air. So, we are now differentiating that it is not reference to the mixture mass, but to the mass of dry air alone. And we do that because in many applications the mass of dry air going through the system or in a system is pretty much constant. The amount of moisture in it goes up and down. So, practicing engineers have found it convenient to use this definition and work with this everywhere. So, this has got the symbol omega. Some books notes you will find the symbol W. So, this is defined as mass of water vapor divided by mass of dry air, which is mass of water vapor upon MdA, and again is, although it is a ratio of two masses, it is not non-dimensional, because what we are looking at is kg of water vapor per kg of dry air. So, everywhere when we do calculations or use charts or property tables, we must put this set of units after the value that we have got. Now, we have seen that both the components of air, which is dry air and water vapor, both are ideal gases. So, what we will do is let us work this up a little bit and express the mass using the ideal gas equation of state, and then we do a simplification. So, let us see what we get. So, this becomes for water vapor M is PV upon RT. So, pressure of water vapor, this is, remember, this is pressure of water vapor and not pressure of air, and TA, which I said that temperature everywhere is TA. There is no differentiation component wise as far as temperature goes. PdA into V upon RdA into TA. And we simplify this. So, this becomes RdA upon Rw multiplied by Pw water vapor pressure, partial pressure, over dry air partial pressure. And both these numbers are known. So, this can be written as 0.287 into kilojoules per kg Kelvin divided by 0.4615 into its units, which is the same, multiplied by the partial pressures of water vapor divided by partial pressure of dry air. And when you simplify this, we get this relation that omega is equal to 0.622 Pwv upon Pda, and if we simplify it a little more, this is 0.622, and getting rid of Pda as Pa minus pressure of water vapor, we get this upon Pa minus Pwv. So, this is an important relation that we have arrived at. And this is something we will use very frequently, that humidity ratio is 0.622 multiplied by the partial pressure of water vapor over partial pressure of dry air, or 0.62 partial pressure of water vapor upon Pa, which is the mixture pressure minus the partial pressure of water vapor. So, what it tells us, it only depends, once Pa is fixed, it is only the partial pressure of water vapor which determines the humidity ratio. So, that is we can rewrite that equation earlier and express partial pressure of water vapor in terms of omega and P A, which is over here omega P A upon omega plus 0.622, and so this is also something which is of interest to us. So, what does it tell us is that for dry air, it means that it is only air and no water vapor in it. Mass of water vapor is 0. So, omega is 0, or you can, to be clear, you can say omega dry air is 0. If you look at the charts in the temperature range that we are looking at, the mass of water vapor, or sorry, not this one, the value of omega is typically 0 to 30 grams of water vapor per kg of dry air. This is a feel for some numbers what it is like. So, what it is telling us is that the mass of water vapor to the total mass of the dry air is of the order of 3%. So, what happens is there an approximation as you will see in some places where we say no, this is so small that I can take MdA almost equal to Ma and use it in the formula for specific humidity. So, numerically the specific humidity and the humidity ratio may have similar numbers, but strictly specific humidity is not the same as humidity ratio or mixing ratio. So, that is what it was here, because mass of water is 3% or less. So, then as far as the number and values go, specific humidity is almost equal to omega, and there are some books who will say that humidity ratio is also known as specific humidity. That is strictly not the case, although by numerical values it will be pretty much very close to each other. So, we must differentiate, and we will keep our bookkeeping clear, because this is going to be an issue that keeps popping up all the time. We will always use the term humidity ratio or at most moisture content in looking at omega. We will not call this as specific humidity. This is a term that is used widely by air conditioning engineers. It has come to be known, and it is much more simpler to use, because as I mentioned, dry air mass in many processes remains the same. So, it is much easier to correlate with omega. Now, we look at the third concept that comes out, and this is called absolute humidity, AH. This is the mass of water in unit volume of air at a given pressure and temperature. So, when you are talking unit volume of air as we have seen, this is our mixture of dA plus Wv. So, we are saying that in a given system, say a sample like that, in which we have both these gases around, water vapor and dry air, then the absolute humidity is grams of water vapor in this per unit volume, which is per meter cube of air as the mixture. So, in some sense we can call this as the density of the water component. Okay, so, this is a definition of absolute humidity. Okay, now, to proceed further, we need to define a new concept, which is what is saturated air, and from there another set of definitions will come out. So, we will conclude this part of the definitions over here, saying that we looked at several properties that came about, and we made an important distinction here between what is specific humidity what we call as the moisture content or the humidity ratio and absolute humidity. And this was preceded by a bunch of definitions where we said that what is air and was subscript A, then we said what is dry air and this we called subscript dA, and what is water or water vapor, we said that we will call it WV. So, we will take a pause at this point and then come back and look at the whole thing about saturation and all the other properties that follow from that. Thank you.